Hello students, my name is Shayan Mitra, faculty member of Department of Electronics and Communication Engineering of Greater Kolkata College of Engineering and Management. Today I am going to taking the class of Embedded System Design, and this one the subject code is EC703B, and this is the lecture number 16. So in the last two lecture, what we have described is how OS works, what is a boot program, what is the significance of OS, uh, what impact it has in PC, server, and embedded system, uh, what kind of OS, what is the basic functionalities of OS. We have understood context switching. We have understood what is a task is. So let's begin with this lecture, and we are going this lecture will be also the continuation of the previous lecture. So let's begin. So in this lecture we will start with the preliminary understanding of synchronization. So in this slide, what you have here is the definition of synchronization. Is that when multiple tasks are running simultaneously, either on a single processor or on a set of multiple processors, it is known as synchronization. Okay, they give an appearance that for each task, it is the only task in the system. At a higher level, all these tasks are executing efficiently. Tasks sometimes exchange information, they are sometimes blocked for input output, and so these are the synchronized. This asynchronous nature of scheduled tasks give rise to race conditions. So if we have to elaborate what is the synchronization is, the task synchronization is that suppose that we have already described that suppose there is a specific application we need to execute, and we have given an example in the previous lecture about the running of a car or driving a car. So during driving a car, we simultaneously handle uh, different kind of tasks such as gear control, brake control, volume system control, window controlling system. So all these tasks are being nurtured or used to confirm one goal or confirm one single goal about the about the driving the car. Driving the car properly is the basic application that we need to consider here. Now all those tasks, those are split. Those are different kind of tasks that has been split in a form of task. So suppose there is in a one specific time frame that all those tasks are performing at simultaneously. So that what here the synchronization comes along with all those things, that for each task is the only task in the system. So it will work. All those tasks are being properly adjusted in such a way that each and every task will act as a only task of the system, and at a higher level all these tasks are executing efficiently. So in different level these tasks in the processor, it gives you the idea that during driving a car you can use the brake, you can use the accelerator, you can up and down the windows. So at that very moment when you are performing a task, you will understand that processor is helping you to perform the task. Basically the system, how the system works is that at higher level all those tasks are working efficiently at a very same time. So you are not going to understand physically that all the tasks those are efficiently working at a very similar time frame. Basically you are going to understand that the moment you use that brake, you use that accelerator, you use that window system, it basically the processor basically working with that. Basically all those tasks are being efficiently placed in that processor in such a way that you can communicate with all those tasks. All those tasks are performing their work at the very same time, and when you're physically availing all those tasks or you're performing all those tasks, you're not going to understand that basically all those tasks are practically running at that very specific moment. So that has been described here. So that is has been said also, that they given an appearance that for each task it is the only task in the system. At a higher level, all those tasks are executing efficiently. Tasks sometimes exchange information and they are sometimes blocked for input output. So this is the thing we are going to understand in this specific section, that when two tasks, they are sometimes blocked for input output. The task, there's when all those tasks are working simultaneously, there is a possibility that they could get blocked for input output. This asynchronous nature of scheduled tasks gives rise to a race condition. So we are going to discuss what the race condition is. Race condition. The ultimate cause of most bugs involving multiple tasks is that the tasks are accessing the same shared data. That's the basic, that the cause most bugs, basically bugs means it's the race condition is involving multiple tasks, is that the tasks are accessing the same shared data. If one task is only part way through updating a data structure, when another task accesses the same data structure, it's a problem. These bugs are called race conditions. The tasks are racing one another to change the same data structure. Debugging a multitasking application is difficult because you cannot always easily reproduce the behavior that caused the problem. You might run the program once and have everything work fine. The next time you run it, it might crash. There is no way to make the system schedule the task exactly the same way it did before. So this is the race condition. It means that suppose there is two tasks that has been processing simultaneously. Now suppose at a very specific moment, or both the tasks have access the same specific data or the same specific data structure. So what will happen? The processor will not going to understand that which task should get the resource allocation. So if it doesn't understand which task is going to get to access the resource allocation, basically to access the resource, what will happen? Both the task will got crash, because the processor goes in an idle state at that situation. So this situation has been known as race condition. Let's go to the next slide. So how it happens? The critical section. Suppose a piece of code that only one task can execute at a time. That's a beautiful example here, that a piece of code, suppose there is a piece of code that only one task can execute at a time. Good. If multiple tasks try to enter a critical section, only one can run and the others will sleep. Simple. Suppose this is the critical section and there are three different tasks. Now suppose if multiple tasks try to enter the critical section, now these three cats are the task. Suppose these three cats are trying to get into the critical section, but only one can run and others will sleep. So what will happen? Now suppose only one task can only one task can enter the critical section. Suppose this one goes into the critical section. The other two have to sleep, and when a task sleeps, its execution is paused and the OS will run some other task. Simple section. Simple mathematical observation is that suppose there is three tasks that could enter into the critical section. Now suppose in the critical section only one task could get entry. So within three, suppose this task, that the cat that goes into the critical section has got the permission or the availability to get into the critical section. So what will happen? The other two tasks will go into the sleep mode. Both tasks will not get executed. So that's what has written here, that when a task sleeps, its execution is paused and the OS will run some other task. Simple. So what will happen then? Now suppose once the thread in the critical section exits, another thread is woken up and allowed to enter the critical section. This task has been completed. It will exit, and another task will get an entry. So In the previous slide, what will happen? These two are sleepy, are slept, and this one, this task is performing. Now after the completion of this task, what will happen? It will go out, it will exit the critical section, and the another task which is in a sleep mode will get into the critical section. So what will happen? Only the one remaining task will be in the sleep mode. Let's go to the next slide. Now here, the mutual exclusion, how it happens? Now a mutex or mutual exclusion works like a critical section. You can think of a mutex as a token that must be grabbed before the execution can continue. So this is the protected resource. Now what will happen? You can think of a mutex as a token that must be grabbed before the execution can continue. So before the execution, the token must be grabbed by any of the tasks. Now what will happen? During the time that a task holds the mutex, all other tasks waiting on the mutex sleep. This is the process where the tasks are sleepy. They are in the mute. They doesn't get the mutex token, so they are in a sleep mode. And only one task that has gotten the mutex token will get into the protected or critical section, and the process, and it will use the data, and the task will be performed. So after the completion of the task, what will happen? Now this is the task that has been performing in the previous slide. Okay, so after the completion or after the task has been completed, what will happen? So there is no need to share the data by this task. So what will happen? This task will exit, and when it exit, it will just put the token free. It will just keep the token free. Once the task has finished using the shared resource, it releases the mutex, and another task can then wake up and grab the mutex. Once the task has finished using the shared resource, it releases the mutex, and another task can then wake up and grab the mutex. So suppose this mutex has been freed up, so one of the two tasks will get the mutex or as a token to get into the critical section. So this is how the mutual exclusion works. So for that reason, so this is the significance of mutual exclusion. So let's go to the next slide. What has been said in the next slide is that locking and blocking, how it works. A task may attempt to lock a mutex by calling a lock method on it. Okay, if the mutex was unlocked, it becomes locked and the function returns immediately. If the mutex was unlocked, it becomes locked and the function returns immediately. If the mutex was locked by another task, the locking function blocks the execution and returns only eventually when the mutex is unlocked by the other task. More than one task may be blocked on a locked mutex at one time. So this is the deadlock situation where more than one task, suppose two tasks, these two cats were who try to grab the mutex coin. How it happens? More than one task may be blocked on a locked mutex at one time. This could happen. When the mutex is unlocked, only one of the blocked tasks is unblocked and allowed to lock the mutex. The other tasks stay blocked. Okay. So this is the deadlock situation. Now we are going to describe so what will happen. Suppose what we have started here. Where we have started? We have started the race condition. What is the race condition is saying is that, so here we are describing that the race condition, the ultimate cause of most bugs involving multiple tasks is that the tasks are accessing the same shared data. So if we just get back to the condition here, that suppose this is the critical section where the data which was needed by these three tasks are being placed here. So this is the critical section where the data which is the data which needs to be shared by these tasks are being here. So suppose this data, one of these tasks is getting into the critical section. It completes it. Other two tasks get into the sleep mode, and they will be in a sleep mode for a while until and unless this critical section where the task has been placed, it completes, the task process has been completed, and then it get out of that critical section. Now after the task get out of the critical section, what will happen? The next task, which one of the tasks, one of the tasks which are sleeping, after the task has been completed, one of the tasks is getting to the critical section again, and it does its job. Now the problem with this, that suppose if we don't have any recognizing system where which of these three tasks is getting to the critical section. So this will be the first, or this will be the first, or this will be the first. We don't have any idea. So this is where the problem occurs. That suppose this task and this task both are trying to get into this critical section at the very same time. So that will create a problem that both of the data, those are trying to get the specific data, the common data which need to be shared, are trying to get into the critical section, but they can't because the processor didn't understand to give that data to which one of the tasks is going to get that data. So to prevent that problem from happening, what we will do, this is the basic process. Now if we don't know that which task is going to complete first, so what will happen? To solve this problem, we come up with a solution which considering a token system. Now this is the token system. This is the token system which is known as the mutex, works like a critical section, and that's why this the process is known as the mutual exclusion. It means all those tasks will be mutually excluded according to the position of the mutex or the token, according to the position of the mutex or the possession of the mutex of the token. Now suppose one of these tasks will have the mutex. Suppose this task has the mutex. So this task will get into the protected resource and will use that resource or share this resource, and during that time both the tasks will stay in the sleep mode. So that has been written here that during the time that a task holds the mutex, all other tasks waiting on the mutex sleep. So after the task has been completed, after the data has been shared, after the task completed, that specific task which is in the protected resource, it don't need that protected resource after the completion of the task, so it will exit and the mutex will be free, and one of the tasks will get the mutex. Now this process is known as mutual exclusion. That's fine. Now but this process is also has its own disadvantage, is that suppose that after completion of this task free the resources and free the token also, and it exited. Now in the next slot there are two tasks which are being in a sleep mode when this task is using that protecting resource or protected resource. So after completion of their task, the protected resource has been freed up, the task has been released, it released the mutex token. So now suppose these two of these tasks need to get into they want to grab the token. Now suppose during the mutual exclusion, in this mutual exclusion there is a problem occurred is known as developer blocked. How it occurs? So both of the tasks want to grab this token at the very same time. So once task has finished using the shared resource, it releases the mutex, and the task can then wake up and grab the mutex. Now suppose both the task is trying to grab the resource that has been described in this specific slide, is that a task may attempt to lock a mutex by calling a lock method. Simple. So in the previous picture where we have 3 cat and the form of task, one of the tasks locked the mutex by calling a lock method. It used it, the task completed, it released itself from the protected resource and released the mutex also. Now if the mutex, after the mutex, suppose if the mutex is unlocked, so the task has been completed, the task has released itself, and the task released also the mutex. So the mutex has been unlocked, it becomes locked, and the function returns immediately. If the mutex was unlocked, it becomes locked and the function returns immediately. Now if the mutex was locked by another task, the locking function blocks it. The locking function blocks execution and returns only eventually when the mutex is unlocked by other task. More than one task may be blocked on a lock mutex at one time, and that is known as the deadlock system. When the mutex is unlocked, only one of the blocked tasks is unblocked and allowed to lock the mutex. The other tasks stay blocked. So now all this written document is trying to say that in the last point is that when the mutex is unlocked, it released it, one task is released. Now only one of the blocked tasks is unblocked and allowed to lock the mutex. The other tasks stay blocked. So that is the best case scenario. This one is the best case scenario. Now suppose both the task has been woke up and both want that mutex at the very same time. Now if they both try to grab the mutex at the very same time, that is the time when it creates the deadlock situation. Now let's explain the deadlock situation. Now what the deadlock means? That mutex provide a mechanism for allowing one task to block the execution of another. Simple. This mutex looks simple. It is basically as it can only be assigned at a specific time to only one specific task. So here the mutex provide a mechanism for allowing one task to block the execution of another. This opens up the possibility of a new class of bugs called deadlocks. A deadlock occurs when one or more tasks are stuck waiting for something that never will occur. Now this is the written document. Now let's start how to understand. Now suppose the problem is where there is a problem where 3 or 4 tasks or 2 tasks want to share the same data at the same time. To solve that problem, what we have introduced a token system or a mutex system, where we will provide a mutex or token to a specific task. That task will take that mutex and get into the protected resource. They use that resource, the task will be completed, will get to a completion. It will release the mutex and release itself from the protected resource. And after that, that specific mutex will be used by another task in the same process of the earlier task. So this is the solution that has been that we have occurred with, which is known as mutual exclusion. So this is the first part. The second part, where if there is a situation where that has been said about the problem that has been occurring here is that mutex provide a mechanism for allowing one task to block the execution of one another. This opens up it is important fact that mutex provide a mechanism for allowing one task to block the execution of another. Now suppose both the mutex has been suppose there is one mutex and both the task is trying to grab it. Now suppose at the very specific time both the task has sent the signal to the processor to get the mutex. Now simultaneously they have set the signal. Now that for the mutex, what will happen? It will just provide the block signal to both the tasks. So what will happen? Both the tasks will think that they need to be the block state because the another task has been performing its own task. So after the completion of the another task, it will get its chance. But they don't understand one thing, that they don't understand one thing, that both the task has been acknowledged with a signal for the block state. Now what will happen? Both the tasks will in the block state. So both the tasks will not get to perform its own operation, and both the tasks will get into the infinite loop where they are waiting for to end another task. But both the tasks are basically staying idle. So this will create a specific bug. This is known as deadlock, and in case of deadlock, both the tasks will get into an infinite loop of waiting or block. So this is the deadlock situation. So we will conclude our lecture today here, and we will thank you.